Hello, my name is Vincent Cuevas.
My name is James Dale.
Today we'll be talking about the paper called Experimental Investigation of Aluminum Oxide Nanofluid on Heat Pipe Thermal Performance by Morajevi and Razvars. To start off, this paper is about observing the effects of aluminum oxide as a nanofluid using it as the working heat pipe fluid. The experiment compared the nanofluid to water and it tested it at different concentrations of nanoparticles along with different power inputs to see the full range of its effectiveness. In the beginning of the paper, they talk about how nanoparticles have been shown to increase the effectiveness. The most common nanoparticles are aluminum oxide and copper oxide because they're the cheapest. Several papers talk about how higher heat transfer coefficients have been achieved using nanoparticles in the working fluid. And the papers talk about how the nanofluid applies to other heat exchangers, not just heat pipes, such as double pipe heat exchangers, double plate, and shell and tube. And the overall goal that was being trying to achieve during this experiment was to decrease the heat pipe thermal resistance and average wall temperature. To start off the experiment section, the paper talks about how the nanoparticles were created. So spherical nanoparticles of aluminum oxide were created using the catalytic chemical vapor deposition method. This resulted in spheres that were between 35 and 45 nanometers in diameter with a density of 3.88 grams per cubic centimeter. After the nanoparticles were created, a nanofluid using 1% or 3% concentration by volume of aluminum oxide was used and mixed with distilled water to create the working fluid. The figure shows a picture of the spherical nanoparticles created for the experiment. The experiment section then talks about the copper heat pipe that was used, which had a 90-degree angle. It had an outer diameter of 6 millimeters and a length of 190 millimeters. The wick was created using sintered copper powder that had 140 to 200 nanometers in diameter, and it was 1 millimeter thick. The condenser section used a water-cooled loop that kept water at 20 degrees Celsius plus or minus 5 degrees Celsius. The evaporator used an electric heater that had a varying heat output to determine the effectiveness at different heat inputs. And then 4 thermocouples with the uncertainty of less than 0.1 degrees Celsius were used. To achieve steady state, the heat pipe was left running for 25 minutes before any data was taken. This figure shows the system of the experiment. As you can see at the bottom, there was the electric heater, which was powered by the power supply that varied different power inputs. At the top is the condenser section, where the water-cooled system was. You can also see the 4 points where the thermocouples were placed. That data was taken to the data logger, which was then sent to the computer.
Now we'll talk about the results that they got from the experiment. Here you can see that they plotted the temperature of the heat pipe wall at 4 locations along the length of the pipe. The first thing you'll notice is the large dip in the graphs. They attributed this to the 90-degree bend in the pipe that you saw in the experimental setup. The next thing you'll notice is that the temperature is generally lower for higher concentrations of aluminum oxide particles in the nanofluid. If a fluid's data points have a lower temperature, that means the heat pipe has a higher performance with that fluid. You can also see that the vast majority of the data points, higher concentrations of aluminum oxide nanoparticles corresponded to lower temperature on the outer walls of the heat pipe, especially compared to water. Overall, it was found that more nanoparticles improved the system the most, regardless of the input power. This graph plots the temperature difference between the evaporator and the condenser as a function of input power to the system. The hump at 30 watts is unexplained in the paper, but it could be the result of error during the experiment, so the experiment should be performed again to obtain more data to see if this is the case. You can see that, for the most part, having more aluminum oxide particles in the nanofluid corresponds to a lower temperature gradient throughout the heat pipe. Having a smaller delta T in the graph indicates that the thermal energy is being transferred at a faster rate since there is less of a temperature gradient. This next graph shows that the thermal resistance of the heat pipe plotted against the input to the power to the system. You can see that increasing the concentration of the nanofluid reduces the thermal resistance of the entire system. This is likely because the particles in the nanofluid tend to bombard vapor bubbles that form in the fluid. Since the bubbles are being bombarded during formation, the vapor bubbles can't grow as large, which keeps them at a smaller size and reduces the total thermal resistance of the fluid. The overall conclusion that they got was that at higher concentrations of aluminum oxide particles in the nanofluid correspond to higher performance of the heat pipe. Since the nanofluid keeps the system at a lower overall temperature than water, the nanofluid has the potential to be very useful in heat pipes for higher temperature systems where temperature might be a constraint. The major cause for these conclusions is that the nanofluid was determined to have a lower thermal resistance than water when used as a working fluid.
For our opinions on the experiment, we believe that the experiment was ran adequately. However, there was some information that we would like to have so that we could run the experiment more. Additionally, there was a slight mention of physical implications. They just mentioned briefly how aluminum oxide and copper oxide are the cheapest of the nanoparticles to create. However, they didn't further explain how much cheaper the difference was between just using pure water. So that doesn't really explain how much of a contender it is to be used instead of just regular water. Additionally, more information was required so that we can repeat the experiment, such as not mentioning the flow rates for the cooling system, as well as the properties of the wick, such as the porosity.
And we also believe that they should run the test several times at each power input instead of a single time. Previously, I mentioned in the graph of temperature difference versus input power, there was a hump at 30 watts, which is likely the cause of error when taking data. So if they took several data points at each power input, this could have been avoided and we could have more insight into the system.
These are the sources that we use for the presentation. As you can see, it's just the paper that we presented on.
And thank you for watching.